So, as Ira said, I love to bring the rubber ducky with me. It's a little bit of emotional support. It's great. It's a little bit cheaper than hiring a therapist these days. So I like to use that, and sometimes when I'm debugging through things, it helps a little bit too. But as Aris introduced me, I'm Faris. I got to keep the F in between the Aris and Faris relationship, so I'm going to take advantage of that. And today, I'm here to talk to you about solving real-world data fetching challenges with Next.js and TanStack Query. And I like to start this talk a little bit with a fact that baffles me. So in 2006, Amazon did a study where if 100 milliseconds of additional load time is added to your website, you lose around about 1% in annual recurring revenue. Today, for Amazon, that would be $3.8 billion per year, just by adding 100 milliseconds. Now, not everyone here is working on a platform where we're earning Amazon-level money through our revenue, but that's really crucial, the aspect of how long it takes for your web page to load. And so we're going to discover how when you're in a world which is unideal, not very favorable, not very forgiving to our web applications, how do we come up with creative strategies using certain well-known tools to be able to come up with a creative solution for something that's used by a lot of people? So a little bit about myself. As I said, my name is Faris. I'm a staff front-end engineer at a company called Small PDF. We build PDF tools that are used by tens of millions of people every single month. I used to be an engineering manager at a fintech called Navro, and I've worked at a couple of companies over here that you can see below. I've also done a little bit of conference speaking at CityJS, which Aris runs, and then I've also had a little bit of experience in the world of connected TV, monetization, growth, fintech, fitness tech, and a couple of other things. I love web performance. I love engineering leadership. We're going to be focusing a little bit more on the web performance part today. And then I also work on some open source projects like Raycast. Who here has used Raycast before? Woo! Fantastic. So last thing is that I'm also the organizer of Zurich.js. I'm from Switzerland. We also have a couple of other Swiss speakers in the lineup today and tomorrow. And we're going to try to keep with Swiss timing today. So Zurich.js is just the JavaScript meetup in the Zurich scene. So if you're ever around Switzerland, the Swiss-German region, this is the place to be if you want to get involved with the JavaScript community. We're up and coming, and we've been doing this for the past couple of months, and it's really cool. So I want to set the stage with the talk because everything requires context. And so the solution that I'm going to be showing you today, the case study that we're going to be walking through, it's not a one-size-fits-all. You're not going to be able to take what I give you, copy and paste it into your solution automatically. Everything's going to be better, and we're going to have a great day. Everything has unique requirements. Our products are all different. They have different use cases, so we have to always keep that in mind. Take things with a grain of salt. You're going to be able to apply certain principles here, but it's not a blueprint. Again, this is also not a tutorial. We're going to be focusing a lot on what are certain concepts that we can apply to actually multiple different tech stacks. It may not just be Next.js that you can use to solve this problem, and we'll discover other ways to do that too. So if you're thinking that we're going to just run through how TanStack Query works or how Next.js works, and that's the only way you can solve this problem, that's not going to be the case. But this is the stack that we're choosing today just so that it's relevant for the conference. And then premature optimization. There is such a thing as you have an application, you're building it, and you put every single performance optimization into it, use memo all over the place, use callback, wrap everything in every performance thing that you possibly can, cache everywhere, and you've got one user. That's not really going to change much for you. I like to give a little bit of a story with this one around premature optimization. I was consulting with a company once in New York, and they were telling me about this really cool product that they were building. And so they had this engineer dedicated to working on their Datadog dashboard. It was the most beautiful Datadog dashboard I had ever seen. They had everything tracked end to end. And I was like, how are you, how many users do you have? And the answer was none. And we don't plan to have users for many months. And so they were putting a lot of time in optimizing something when there was no real use case for it. So we always have to be very pragmatic as engineers and think, where do we put our energy? Where are the bottlenecks? So what's the problem statement for today? What are we doing? We're putting our tech lead, our product manager hats on, and we're thinking about a certain problem space. And the problem space is, what challenges do developers face in creating a seamless user experience due to complex data fetching and management? But I'd like to take also one step back on that problem statement. How can we build optimal solutions in suboptimal conditions? Because we rarely have optimal conditions, except when I'm on localhost, I've got an Ethernet connection, everything works wonderfully. But no, if I'm on a mobile connection and I'm going through a train and I'm switching, for example, I was on the train from Switzerland over to Italy, passing the borders, connection cuts. things happen. It's not ideal. Sometimes you're on an airplane, you're on a long-haul flight, and you're connecting in-flight Wi-Fi. Half the websites don't work. It's a nightmare. Now, are we going to design all our websites airplane first, like we do mobile first development? No, that's not the point. But we have to think that our users are not always in the exact same place that we are. There's another question to answer. Why bother? Now, the first 0 to 2 seconds is the golden window for capturing users. Anything longer than that has a significant impact on your funnel. Actually, if you increase from 2 seconds to 10 seconds, you have a chance of 123% bounce rate. That's a massive difference. Every single second counts really after those 2 seconds. But for example, in the case of 1 to 3 seconds, it's just a 32% bounce rate. So that number jumps up really high. So we really have to capture people as soon as possible. And there are a couple of tricks on how to do that. Now, 14 kilobytes is also an interesting number. 14 kilobytes is the exact amount of data that fits within a single TCP packet, minimizing round trips. And what's interesting about 14 kilobytes is that if you just add one singular kilobyte to that network request, it can increase the amount of time it takes to resolve by 612 milliseconds, just for that singular kilobyte. That's a massive difference, and I like to visualize it like this sometimes. So you want to see a website, you've got 14 kilobytes in that single network request, and that's just not your HTML. That could be your JSON payload, your CSS, or whatever it is, your individual network requests. 14 kilobytes, one packet, it's all resolved, happy days. 15 kilobyte website, you resolve the first 14, you go for another round trip, ask for the rest of it, you get the final kilobyte, and then you're ready to go. And so sometimes optimizing your network requests for things to fit within that 14 kilobyte space that we have can make a really big difference. You're going to see that journey through a little example that I have later on. Just to give a little bit of an example, if you go on the Twitter or X homepage, there are around 300 plus requests made. Whether that's static assets, images, JavaScript, so on and so forth, JSON requests to view your feed, there are a lot of requests going on. Not all of them are equally important. But you have to optimize every single one of them if you want to catch your users with the first things that they're going to see. So talking about the technologies, we mentioned already Next.js and TanStack Query. If you're not familiar with those, I'm going to give a brief overview. So Next.js, if React is the library, Next.js is the framework. So it helps us a little bit with server-side rendering, pre-rendering pages. You can also use static site generation, which is great for documentation-based websites or SEO-prioritized websites. It allows for file-based routing, which sometimes is a little bit questionable. And then also API routes, which is something that's really cool. So it's a full-stack framework. You can develop your front end there, and you can also have edge functions deployed as little express handlers. So that's something that's really cool in Next.js that allows you to be really flexible. Then TanStack Query. So TanStack Query, otherwise also known as React Query, it's actually agnostic, so you can use it with multiple libraries and frameworks. It's a powerful asynchronous state management library. And I like to say those words really slowly because a lot of people think that it's a data fetching library. And that's not necessarily the case. React Query or TanStack Query is just really good at asynchronous tasks, and that so happens to be data fetching, and that's what's primarily used for, but it actually serves as a global store. So instead of plugging it into Redux or to Zustand or Jotai or whatever else, it actually can serve as its own global state management system. And that's something that's really powerful to take into consideration because what I've seen sometimes in some code bases is you fetch something with React Query and then you put it into a separate state management system. And that's not how it's meant to be used. A couple of cool things with React Query is that it allows for automatic caching and background updates, something very difficult to achieve. You may have multiple pieces of data on your website, and if you have a form that you've changed some information with, you may want to update a list and refresh some information later on because something changed. So it's really cool with invalidation of caches and refetching things. Also, optimistic updates. So this is important for UIs. Let's take the example of X. If you want to like a post, an optimistic update is you change the UI. You increment the like before you actually have the network request resolved. It shows a more reactive UI, something that's a bit more of an intuitive experience. So React Query is really good at helping us build those kind of experiences. Then pagination infinite loading. If you ever looked at Stripe documentation, you just keep on scrolling and scrolling and scrolling. And so you can't load all that stuff in one go. It really helps to separate those things in different blocks and load them at a time as they get into the viewport. And then you have a couple of other things you can do with Next.js, such as prefetching that we'll look into later on. And then, as I said already, built-in query and validation, which is not something easy to do. I want to also talk a little about different API types that we interact with. So sometimes we interact with public APIs. That may be the Star Wars API. That's one that exists that's public, and you can fetch information about Star Wars characters. That's an API that if I use it, I have zero control over it. It's deployed by somebody else. They decide, what the open API spec looks like. They decide the interface. I can't go and tell the creator of that API to go and change something because it suits me better. So there's no control over that. Then there are internal APIs. These are the APIs within your product teams where you have a backend that's dedicated for your front end. And so when you have an endpoint that doesn't service your need, you're able to just ask your backend team to create a brand new endpoint or change the data structure. There you have flexibility. You have no third-party dependence or external dependence on that API. And then you have partner and product APIs where things get a little bit complicated. You may have APIs that you're designing internally, but they're meant to be paid service products that are used externally. So you're not able to change the APIs to fit your front end's use because you have deprecation policies you need to follow. You have breaking changes that you can't integrate so easily. You have to inform clients maybe sometimes 6 months in advance. So you can't keep on changing the backend to your needs if it's something that you're actually selling to somebody else. So we're going to go through a little bit of a case study that I like to start with calling bare bones data fetching. So we're going to put our product hats on, and we received this ticket, this Jira ticket that explained this problem. And this problem is also going to come with limitations. Again, we're designing for suboptimal conditions. And the reason I talked about the different types of APIs before is that the API I had to deal with in this case study was a partner API, which meant that there were third-party dependents. Other people were using that API. It was a paid product. So I had no control over that API, even though it was our backend teams that were designing it. My front end had to consume it, but I could not change the endpoint as I wanted to. So what's the scenario we have? Our front end team needs to design a dashboard chart that displays the distribution of birthdays for the top 5,000 users in the system. Key information, 5,000 users. That's why it's in bold. Data source. The data is available via an API which returns a list of users with all their data. Sounds fairly simple, stuff we deal with every single day. But the limitation is the backend team's unable to provide a new endpoint or a data warehouse, which would be another solution that returns the required data format, and there's a limit of 1,000 users for every single request returned. So we already start thinking a little bit about how we can solve this. So we have 5,000 users we need to get data for, but I can only fetch 1,000 at a time. So the first thing we start thinking of, like, okay, I need to make multiple requests to get this information. That's not really ideal. But how do we build an architecture? So we're going to start with something really basic, and we're going to migrate this towards a more optimal solution given the limitations we have to deal with. So what does the first architecture look like? We've got a user interface right over here, so that's your client-side application. And so because we need to get 5,000 users worth of information, we make 5 parallel requests. We're not doing that sequential, we're doing it parallel. That's already some IDF and optimization. We're doing this all at the same time. So once I make these requests, the requests shoot off. There's a loading state. We want to show our user that something is happening. We're working on some information. And there are 2 things that could happen. One is an unhappy path. Something goes wrong. So we persist the loading state. We still say that we're working on it, and maybe we implement some resilience pattern of some sort. Something very basic like a retry pattern. Maybe that's custom logic. We're not using any libraries at this stage. So either you retry all the requests, or you just retry the ones that fail. Then, in your happy case, your data does get returned from all 5 fetch requests, and you map the data. The data is not in the format you're going to be consuming and sending to your components, so you need to change it up a little bit, change the data structure. So you're going to map the data into what you want it to be. Then you're going to set it in state, and we're saying local state for this example. You're going to render your UI, and then something may happen is that in the JSON state, if you haven't optimally handled it, may cause a re-render of a component. And if this fetch request is happening in your use effect, if you have something unrelated, let's cause the state change that is now affected in a JSON component to rerun its use effect, it's going to run these 5 requests all over again. It's going to keep on doing this, even though it may not even have to. I don't think people's birthdays are changing every couple of seconds or every couple of minutes. So what's the problem we land ourselves into? 429, too many requests are making. The backend server is going to say, this is not my problem. You're making too many requests. I'm done. I'm tired. I'm checking out for the day. So it's going to stop responding at some point and give me an error. Now, this is what it may look like. You created some sort of a use fetch hook. Underneath that, it's using a use effect. You have some sort of a function that does the parallel request, like this get fake data. It returns a response, and then we do the mapping effort. Okay, we want to get birthdays by month. So we pass the response there, we get the birthdays by month. Okay, we need chart data now because we're going to display this in a chart. So I'm going to pass the map data, and I'm going to return chart data. And now we're going to set the data in state. Something pretty standard. I'm sure we've all done that. And so we're going to look at our first demo of all this effort of making the 5 requests, mapping the data, set it into state, and maybe an adjacent state request affecting this, and see how long it takes or how much of a pleasant user experience it is. So if we see this demo, we worked with some important UI UX designers on this, so it's absolutely beautiful, right? It takes quite some time to load. So the loading spinner is going for a little bit of a while. If we inspect the network requests and we look in the network, what I'm going to do over here is I'm going to click hide and show. So this is a state update that's affecting the requests. It's going to make 5 of them. And you can see it's taking quite a moment to resolve all of them. And I'll show you something interesting. Once we click on one of them, we're going to go and look into the payload. And when you look at the payload, you're going to be seeing a lot of information that's actually quite useless for us. Longitude, latitude, phone number, bio. This is information we're not displaying. It has no use to us. So why are we fetching it? This is just adding bloat. And again, every time I click some sort of a button that causes a state update, I'm refetching data I don't need to. And this is sometimes a pattern that's quite often seen in certain applications. So if you didn't count every single network request and are you very good at maths, it is 2.3 megabytes of payload. That's a lot of information for something that we're barely using a lot of it. We're actually only using 73% of the data. We actually have 73% of the data unused. So we're using only a very small portion of it. Now, what are key factors in this initial solution that we've tried to go for? We have some custom retry logic. So that needs testing, it needs maintenance. Sometimes it's subject to bugs. That's why I want to offload these efforts sometimes to another library that handles it. There's no caching by default. So again, you run into this problem where every time you're clicking that button, you're not going and fetching information from a cache, you're going directly to the server. State management isn't easy, especially if you're using context providers or local state. That's why sometimes we go for global state management solutions. And then you're doing this data mapping effort on the client side. And so you maybe have to do these use callbacks and use memos because every time there's a re-render, you don't want to recompute this information. And the payload's not optimized. We're fetching too much information for our needs. So I'd like to introduce a little bit of a pattern over here. This is called the Backend-for-Frontend pattern. It's our best friend forever. And this version of it is called the transformation bridge or the aggregation proxy. So it's a proxy, something that sits in the middle that aggregates information for us before passing it along. And it's a really nice pattern to use when you want to empower your front-end teams to change data from a backend they have no control over. And so what's cool about it is that you have adaptability for your platform requirements. Maybe you don't have the singular web front-end, but you actually have a mobile application, a TV application that all interact with the same backend, but they have the same data structure requirements from the final response that they need to receive. Decoupling of concerns is something really important. You don't want to pollute too much of the same things in the same code base. You want to have separate stuff. And then you can optimize performance. You can have a team just dedicated to working on this proxy and dedicated to figuring out how to get the data mapping to happen as fast as possible on this proxy before it's sent over to the front end. So what we would do is all that data we initially received, we're going to condense it into just the minimum viable amount of data we need to ship and show the information to our chart. And so what does this change in our architecture? So now instead of those 5 requests, we're going to be making a request to our proxy. So this is going to be, for example, your Next.js API handler that you would create. So you make one request, we do the same things we did before, one loading state, and then it's your proxy making on the server side those 5 parallel requests. Same case with unhappy state. With the unhappy path, something may go wrong. You'll fail and return an error code to the client, and you may handle some retries however you want to. Still some custom logic. Happy path is you receive the data back from the 5 requests, then you map the data on the server, and you send data to the client only whatever the client needs. You set the data into state, you render the UI, but you're still presented with the exact same problem where if I make a state change and it affects this fetch request, I'm going to go hit the server again, which is going to make those 5 requests, and I'm back to this 429 story. So what will this change look like in this little hook that we created? We're going to condense it and only just make one fetch request instead of those 5. So now we're offloading the effort onto this proxy that we've built. So a couple of changes with this new version of the architecture. We've done a little bit of failure isolation. Instead of handling the failures on the front end, we isolate everything to this proxy. Then we also have clear separation of concerns with code-based management. So I don't have to have all the logic on my front end. I can separate some things out in terms of how I want to do the mapping on this proxy side. The data mapping's done there too, so I'm only sending the information that I need to the front end. And so then the payload can be optimized. And that's something that's really important for caching sometimes. Because if you're caching in local storage, if for offline cache, local storage has a limit, 4 megabytes. You can't fill that up too quickly. And so if you optimize things from the get-go, you're going to have a lot more liberty with how much you can put into that cache. So let's look at demo 2. Just by making the singular fetch request, and it's still making the 5 requests under the hood with no caching, are things faster? Was that a little bit faster? Yeah, cool. But we haven't done too much. We've just offloaded things onto the server, onto this proxy. But we're just getting the information we need already in the format we needed just for the chart. And what you see over there is we've condensed now that 2.3 megabyte payload into a 666 byte payload, which in reality is actually a 99.9% reduction. Now, again, is this a boilerplate you can apply to every single pattern, you're going to get 99% performance gains? No, but in this use case, that's actually what happened. And what's even more interesting is that no matter how much data you return back from the original backend where you're making the 5 requests, if you add 10 requests, 20 requests, what you send from the proxy actually never changes because it's the mapped chart data. So you're going to consistently keep 666 bytes as a response. And so why is that interesting when it comes to network requests? So if we take this 2.3 megabyte payload, what we were originally fetching on a normal Wi-Fi connection, that takes 210 milliseconds. That's not too bad. Go all the way down to a 3G connection in some rural areas, that takes 9.5 seconds. That's an unacceptable user experience. And so we have an exponential increase in the amount of time it takes to resolve the request every time we want to increase the amount of users we want to return for the chart data. That's a big problem. But now if you look at 666 bytes, which is going to stay consistent no matter how much data I increase from the proxy that I'm fetching, download time on a Wi-Fi connection is 0.59 milliseconds. Going to a 3G connection, it's 7.6 milliseconds. It's a massive difference in being able to shrink that payload and just send what you need to the front end. And an interesting topic is that now, okay, I'm going to be creating this proxy, so I'm going to have to deploy now some serverless functions or an infrastructure service, whether it's your EC2 instances or whether you have to deploy, your cloud edge functions. And so the topic of ingress and egress becomes really important. Ingress is data that's coming into your system or network, and egress is data that's coming out of your system and network. And so when you have a deployed server or deployed edge function, you have to be concerned about how much money you're paying for data coming in and data coming out, because that's expensive sometimes. And so with ingress, that's actually not charged from cloud providers most of the time. Egress is what's charged. So you can fetch as much data as you want to coming into your service. It's only going to charge you on the data fetching out, and 666 bytes is a really small amount. So you're not going to have a lot of cost complexity with this. Just to get a little bit more into what these two separations are, the function as a service and infrastructure as a service. Function as a service, as I mentioned, you have an ingress bandwidth of around 1 to 5 gigabits per second, massive compared to the connection you would have on a mobile phone. And this is the typical example of your AWS Lambdas, your Vercel Edge functions, so on and so forth. Of course, a little bit of the disadvantage with the function as a service is the fact that you have cold starts that impact it sometimes, and you have to keep it hot. That's why sometimes people will opt for infrastructure as a service, which may have a different cost impact, but then it's always running hot, so you don't have that initial start load problem. But again, for example, infrastructure as a service has 2 to 25 gigabits per second. Much, much faster. So if we look at this chart over here, if I'm using this infrastructure as a service or function as a service, even just for getting that 2.3 megabyte payload, it's 80 milliseconds or 50 milliseconds. On a Wi-Fi connection, we saw that was at an unacceptable pace. If we now go all the way and quadruple the payload I'm fetching from the proxy, that I'm going to be turning into that 666 kilobytes, on the function as a service, that's still 320 milliseconds, 200 milliseconds on infrastructure as a service. If I were to do that on a 3G connection, you're waiting over half a minute. That's just never going to work in a real world application. That's your user's never going to want to use your application. So TanStack Query, already introduced it a little bit before. You can look at all the features that it has, but it does a lot of things for you. It's backend agnostic, auto caching, really cool dev tools. It helps you a lot to solve some of the problems that we just faced in this case study. And so if we implement TanStack Query now, so we don't have to do the retry manually. We're not doing all the caching ourselves. We can now offload it onto this third-party library that helps us out, and we don't have to do any testing for it. It comes with a lot of things out of the box. So we're doing the same thing we did before. We're making one request from the client side, and we're doing a loading state. Now, a loading state is not something we have to control with our use states. It's something that React Query out of the box will track for us. So something, again, we don't have any overhead with. Then on the server side, we're making 5 parallel API requests. We may have the unhappy path. It fails, returns an error. React Query is going to handle the retries. Not only the retries, but out of the box, React Query can even implement an exponential backoff pattern, which means that you can, in one line of code, tell React Query that, hey, you don't have to retry every couple of milliseconds. You can give some breathing room. So I fail once, wait a second. I fail twice, wait 2 seconds. Allow for the server to recover. But now if I'm on the happy path, I map the data on the server side. I send the data to the client. I cache it now for the first time. That's, again, out of the box with React Query. And you can do offline cache. You can do memory cache. Now, React Query derives the state from the response. I don't have to do anything special about it. We render the UI. And now, even if I have a suboptimal handling of states in adjacent components, if I re-render the UI, React Query is going to be like, hey, check in your cache. Do you already have this information? Is it valid? Cache is hit, let me render the UI, I don't bother fetching anything again. If there's a cache miss and I deem that the data is no longer valid, I restart the process. But now we're starting to help this whole 429 issue where we're unable to get the server to have some breathing room. Now, what will the request look like? You use query, which comes out of the box as a hook from TanStack Query. So you're just passing it query keys. That's how it's going to store and understand what cache it's going to be getting it from. Stale time, how long is this data valid? And then you pass it the fetch request that you're going to be making. And so now what are the key factors with this version of the implementation? Third-party library, React Query controls most of it. The loading states, the error, deriving the response. Then caching is optimized. And it can be done with multiple strategies. As we said, offline cache and in-memory cache. We limit the refetches with re-renders, and we have resilience patterns out of the box. We can go one step further. I know I'm running out of time. Query criticality. Now, we saw how with Twitter or X, there are 300 requests made. Are all of those 300 requests equally important? I don't think so. If we look at these two requests, auth requests, and a request for chart birthdays, it's a lot more important for me to understand if my user has the right groups and scopes to be authenticated to use my platform than it is to get the birthday data. I can live without the birthday data, but if I'm showing information that's not good from a security perspective that they're not allowed to see, that can be detrimental to my business. And so what you can do with React Query is you can actually build helper functions into it that allow it to decide what the criticality of each query is. And so if one query fails, you can fail the entire application because it was critical to it. If you don't know the groups and scopes of your user, you don't want to show any UI. If it was an optional query, you can still show the UI and you can try to recover on the client side. So am I out of time? Okay, I'm going to show one more demo. I'm not going to go through this one. I'm going to show, this was the code on how to handle maybe optional queries. So you can do this on the server side. You can design these helper functions. But in this demo, what I'll show you is that for the first time, we're using prefetching on the server side with Next.js, and we're trying to prefetch the information. If we fail to do so, we time out on the server, and we try to recover on the client side. And this is the final implementation of the solution. So I try to refresh the page, and you'll almost nearly instantly see the data. And it's cached for the first time, so we don't refetch it necessarily. Over here, what I'm changing is the timeout. So we originally gave ourselves 2.5 seconds to fetch the data, and now I changed it to give myself 500 milliseconds to fetch the data. So on the server, if I was unable to fetch the data in enough time, we don't want to block the user and show them a white screen. We want to be able to give them interactivity as soon as possible. And so what we did is we bail the request on the server, and we go on the client and try to recover it and show a loading state. Cool. That was a lot in 35 minutes. Thank you for your time.